My name is Stephen Stigler. I'm chairman of the statistics department, and it is my pleasure to be introducing David Donoho to you today. David is the Ann T. and Robert M. Bass Professor in the Humanities and Sciences and Professor of Statistics at Stanford. About 4 hours ago, he received the honorary degree of Doctor of Science, one of 4 honorary degrees that were awarded at our 500th Convocation this morning. He was honored for that, on that occasion, he was honored for work that has already had a great impact in statistics, in computer science, and in applied mathematics. And in his talk this afternoon, he will discuss for a general audience some of the ideas underlying this work. And this will give a better introduction to his work than I could hope to give, and so I will not be long. But I will say that if you encounter any publication dealing with the expression, summary, and analysis of high-dimensional data, particularly publications invoking phrases like wavelets or compressed sensing or oracle methods, then if the author does not cite David Donoho, it's a sign the author has not done his or her homework. David has been at this subject since the beginning of his career, and one of his earliest productions was a computer program that he wrote for the very first Macintoshes called McSpin, that would put three-dimensional data in motion, making patterns visible that would otherwise evade the eye. Today, he will, I believe, take us well beyond that third dimension and show you with his characteristic lucidity just how to think about and how to see answers to problems that even a decade ago were dismissed as impossible. It's a pleasure to introduce David Donoho.
Okay, well, thanks very much to the statistics department, especially to the university, which gave me this nice pen and the hood and the degree. I've actually been fortunate enough to spend some time at the University of Chicago in brief visits over the years, and at one point my wife was on the faculty at GSB. We have very close friends on the faculty here, and it's really, really a pleasure to come and speak to you all today. The particular topic that I'm going to speak about, I'll try to begin in a leisurely way. Now, at lunch, Steve Stigler was talking to someone and promising that this was going to be a highly graphical talk. And it's true that ordinarily I use lots of things that illustrate my points graphically. However, I figured if there's anywhere in the world where I can be serious, it's got to be the University of Chicago. If there's any place I can get away without pictures, it's got to be here. So actually, I'm not going to have as many cartoonish things as I ordinarily would. I hope that's still okay. Okay, so here's a question that probably a significant number of people in the audience have thought about. If you've ever had an MRI scan, say because you're having knee trouble or because there's a hip replacement that's being considered for you, or for whatever other reason, you were probably confined for a great deal of time in an uncomfortable way and perhaps in a claustrophobia-induced state of fear. You wondered about this very question. Why do I have to be confined this way for as long as it takes? And the straightforward answer, which is pretty much accepted in the radiology profession, is that the real culprit is not the radiologist or the physicist, but it's those darn mathematicians who have this thing called the fundamental theorem of linear algebra, which basically tells us how many pieces of information we need to solve a system of equations. So let me say a little bit about that. Here's an example of a system in 2 equations and 2 unknowns. So the equations we write top to bottom, and the unknowns are these symbols x and y. And as it turns out, there's one and only one solution to this system of equations. And when we say we're solving a system of equations, we're trying to find the values x and y that give us that solution. And many of you will have encountered this in school algebra, and you may not understand what this could possibly have to do with getting the radiologist to look at your knee. However, it is really involved, as I will say. Okay, there's a geometric way to understand why two equations and two unknowns can have a unique solution, and it's by basically graphing, associating each one of the equations with a line in the two-dimensional space of x, y's, and looking at the solution set of each individual equation. You see that the solution set in this case is a line, in that case is a line, and those two lines intersect in a point. So going back to the Greeks, we learned that there's either no solutions or one solution from just the basic things we were taught in school geometry. So you can understand this either algebraically or geometrically. And the different possibilities, if we kept two unknowns and went to more equations, we would find that, well, here there's not enough information to say where we are, because there's only one equation and we're just somewhere on that blue line. Here we have two equations, we're at one specific point, and we go to more than two equations. Generally what's going to happen is we'll see an inconsistency such that there isn't even one point that satisfies them. And I think many people have heard about this in school algebra, and it's pretty standard. Everything we were just talking about can be written out symbolically, of course. Now, if we go to higher dimensions, we can consider say, a case with three unknowns and three equations. So then each equation then becomes a linear plane in 3 dimensions, and each of the three equations is satisfied along one of those planes, and those three planes intersect in a point in complete analogy to the case we had before. Generically, there will be one point of intersection, although obviously we can, by analogy to the previous cases in 2 dimensions, make the planes all parallel so they have no points in common, or make various kinds of other intersection properties hold. Now, if we only have 2 equations and there are 3 unknowns, then what's going to happen generically is that there's what we could, a line in this 3 space, and any point along the line is going to satisfy both of those. So this is just sort of a geometrical rendering of the whole situation. We want to go well beyond what we can visualize in 3-dimensional space and talk about very high-dimensional systems of equations. This is a common trend in modern mathematical sciences, and if you're not accustomed to it, it may seem a little strange at first, but really it underlies the whole of the information society that's developing around us. So it's this viewpoint of going into high dimensions is just as important to things you use every day, whether they be Google or digital cameras or any other kind of modern media experience that you're having. But anyway, a system of n equations in p unknowns we could write out like this. So the a's are the coefficients, the unknowns are the x's with subscripts, and the specific values on the left-hand side are particular values that determine the precise thing we're trying to be equal to. So that's a system of equations, and there's a general phenomenon which is captured in its the most fundamental phenomenon of linear algebra. If n less than p, there's no unique solution. Instead, there will be the analog of one of those lines, but it could be a higher dimensional set, could be an affine subspace, it's called, a kind of a plane or a line or some higher dimensional set, all of whose elements could be solution of the system. On the other hand, generally speaking, if we have n equals to p, there will be one solution. And by generally, I mean for most arrangements of those a coefficients, you would end up with this particular phenomenon. And there's a way to make most precise. And then if n is bigger than p, generally there's no solution. Again, generally has to be taken in the right sense. Now, scientists and engineers use this every day, all the time, and it's built into their viewpoint. And often what they're really interested in is this particular case. They have something they want to determine, and they set up a bunch of equations with just enough elements in their system so that they get a solution. This is an important tool in science. And this is often called parameter counting. Do we have enough parameters to determine the problem? Okay, to simplify things, at least visually, we can use matrix algebra and write the system out that we had before as a matrix product A times X. And all that that means for our purposes here is that the way that I wrote the system 2 slides ago, that's exactly what y equals A times X means. You don't have to know more than that. The table of those coefficients is called an n by p matrix, and X is the set of unknowns here, p by 1, and y is the set of left-hand sides here, n times 1. So whenever I write that out, what I mean is that what we know in this system is y and a, but what we want to know is x. We want to determine what is the x which gave rise to the y that we have. And we say that the system is underdetermined if n is less than p. And that's just in case this table of numbers has the property that it has more columns than rows, or is kind of a wide and short matrix or table rather than a tall and thin one, for example. Okay, so if we go back to the original question, why do I have to sit in that MRI scanner for so long? The answer, as I said before, was the fundamental theorem of linear algebra, which comes out in this case to the radiologist wants an image that's going to have something like 10 to the 6 pixels in it, and he's going to look at that and then determine if you have a tear on the meniscus of your knee. And so he has to get those million pieces of information that go to make up the picture. So therefore, by the fundamental theorem of algebra, you can expect the MRI scanner has got to gather p pieces of information. And that's what it's so patiently doing, making all those weird noises of kind of groanings while you're sitting inside it. It's gathering all those different pieces of information, the million things that it needs to make the radiologist picture. Now, there are fancier ways to say this, but I prefer to not. So we could say Nyquist, Shannon, Kotelnikov, Whittaker, lots of different streams of research led to the same conclusion, but in the end, it's the fundamental theorem of linear algebra. Okay, on the other hand, we know that underdetermined systems of equations are important all over the place, and in some sense, we believe that they get solved all the time, and I'll give you some examples. In digital communications, you could easily arrive at the situation where, roughly speaking, you've got a system with a capacity to make n measurements on incoming signals, and there's somehow p cell phones running around out in the outside world, and n is less than p. There's a fixed number of elements that are able to make a reception, and there are many, many potential cell phones. There must be 150 cell phones in the audience here. And the local cell tower might not be able, per time slice, to make 150 measurements. Maybe it can because it's a university and so on and so forth. It might be more densely provided. But the principle would apply maybe on a larger scale if 150 did not already satisfy. Another example would be that in genomics, we might collect data from a gene expression array that for each patient gives us 30,000 pieces of information about gene expression, But we might only be able to find 100 patients who would be willing to enroll in the study, maybe 50 affecteds and 50 controls. It might take us a lot of time and effort in order to find them. And so if we think about a model that says that there's a relationship between gene expression and the relevance of the gene to an output, and the output that you see, we would have a situation where obviously it's an underdetermined system with only 100 patients. We can't hope to do this thing. And yet, just like in the cell phone case, research goes on and people believe that something's going to come of it. So they're not so intimidated by the fundamental theorem of linear algebra in either of these fields. Why do you have to sit in the MRI scanner so long? Okay, well, the key thing that's going on in those fields is that most of the variables that are the unknowns are inactive. They're implicitly zero most of the time, and you don't have as many as p active things. You have much fewer than that. So for example, in the cell phone case, most of the people's cell phones are not going at full bandwidth all the time. They're just sitting in your pocket, and every once in a while they check in with the cell tower. And so the rule is, on any given time slice, a very small fraction of active elements. The same thing we hope to be true in genomics. That is, although 30,000 genes could conceivably be implicated in any given condition that we can think of, let's say some dreaded disease, what we really hope is that it's only a few genes that are involved in the particular condition. And as far as we know, that's the case for most conditions we would be talking about. So there's this concept of sparsity that's underlying many of the successful applications where it would seem that we have p bigger than n, or fewer equations than unknowns. So here's a fundamental theorem for situations with sparsity. And I should say that it's not that the system matrix A is sparse, it's that the solution is sparse. So imagine that you have a matrix that has this underdetermined character. For its shape, it has fewer rows than columns. And imagine that the underlying object of interest is a vector x0, which has only k non-zeros. You have this system, then it turns out that there's only going to be one solution that you can write this way, having k or fewer non-zeros, provided k is sufficiently small. In the generic case, so the generic is an important thing to mention. So quite generally, if there really is a sparse solution to this thing, and you're able to verify that this matrix has generic properties, then in principle, you ought to be able to get it that there's only one particular sparse solution that could work. However, this is a completely existential result and not of much use for any application. It's just simply a reminder that maybe there's hope. The reason that we can't use this result is that it's well known that looking for sparse solutions is equivalent to a lot of very, very hard problems in combinatorial optimization, things that have resisted attempts at rapid solution for decades by very able people in theoretical computer science. And as far as we know, if you really wanted to solve a system and find the sparsest solution, the only effective way to guarantee that you do exactly that is to enumerate all possible sparse subsets containing anything from 1 up to as many as p minus 1, and just see what you can actually use to actually satisfy. And there's an enormous number of those subsets, so that you really don't have a chance of doing this on a digital computer if the system is at all big. Now remember that in the MRI case we were just mentioning, the system could have 1 million entries, and so there's just no hope of 2 to the million evaluations of things. That's just way out of reach. Now, there's an interesting phenomenon that happens, which sometimes brings the possibility of finding sparse solutions within reach of computations that we agree to be feasible. And that goes like this. We can write out the problem of finding the sparsest solution to a system of equations, which we know from a previous slide would be what we're looking for, in the following formal way. We're looking for a system of equations, a solution to that system, and among all those solutions, we're looking for something that has the smallest so-called L0 norm, but it's just a count of how many non-zeros there are. So it's a measure of sparsity. What's the sparsest solution? We know that that's hard in general. On the other hand, if we do the innocent thing of replace that 0 by a 1 so that this becomes the sum of absolute values, that's something that can be solved by convex optimization, in fact, linear programming. And it turns out, rather surprisingly, that in many cases the two problems have the same unique solution, so that there's exactly one solution to this problem, and you can do it by linear programming, which is a method that's taught sometimes in undergraduate courses and is a completely standard method. There's a lot of literature on this topic in the last 10 years giving examples of cases under which these two things will have the same solution, and many, many different ways of articulating this equivalence have been found. So specific conditions under which these equivalences will happen. But the key thing is linear programming can be done relatively rapidly. We consider that to be a problem that's within reach. And this seems to be something that will be forever out of reach. But on special cases, we can do this one instead. Now, I should say, I'm taking this at a very abstract, serious level, but this, the issues that we're talking about come up in many related fields. So in statistics, there's a method called the lasso, which involves the use of L1 norm penalization of a sum of squares. And essentially the ideas I'm talking about here in this talk are closely related to why the lasso would work in many cases. So I'm taking a very abstract and austere point of view, but the underlying phenomenon impacts other fields and less abstract situation. So here's an empirical result which I'd like you to keep in mind. We set up random systems of equations where that A matrix is generated by a Gaussian matrix, and unfortunately the notation is slightly changed here, but capital N is the new P, just for this slide only, I hope. And so we make a matrix that has a given aspect ratio where N is the height and P is the width. So the ratio of those two we're going to call delta. I guess these are backwards. Anyway, the aspect ratio is going this way. This is a matrix that's square, and this is a matrix down here that would be extremely wide and short, okay, because we're measuring the number of rows relative to the number of columns. And here, this is a vector that's very sparse, and this is a vector that's very dense. And what you see is the result of the following computation. Solve the L1 optimization problem that I talked about on the previous slide for this random problem instance that has a given amount of sparsity and where there's a given amount of underdetermination of the system of equations. And we have those parameters about the sparsity and the underdetermination, and we can dial them into any combination we want in the unit square. We can be very non-sparse, and we can be very well-determined, etc. Okay? And it turns out that there's a frontier indicated here such that if you're below that, what you see is exactly the unique solution phenomenon that I was talking about. You get back a sparse result by running linear programming, and above that frontier, you don't get it back. and there's a kind of catastrophic failure. What you get back has nothing to do with the true underlying sparse solution. And the red curve is a theoretical curve which Jared Tanner and I have worked on computing using geometric methods I'll talk about in a minute. And the blue curve is just some ragged empirical approximation of what happened on this data set. Now, in that particular instance that we had on the previous slide, we were talking about solving L1 minimization. But in given situations, you may know a lot about your problem that you want to bring to bear. And an example of something you may know is that the unknowns in your solution happen to all be non-negative. So in that case, you might consider looking for the sparsest solution that's non-negative. And then there would be a slightly different corresponding so-called relaxation that amounts to a convex optimization you could solve. It's again a linear program in this case, imposes non-negativity, but instead of the L1 norm, it's just minimizing the sum of the elements. It's a standard linear program. And so Jared made this computation where a very similar thing was done, and we ran on random problem instances with a given amount of indeterminacy and a given amount of sparsity. And what we found is that there was a rapid transition from something where it always worked to a place where it never worked, meaning the sparse solution was always found and was never found. And it happened at that red curve that's indicated there, which Jared and I published in a paper in 2005, PNAS. Okay, so that's just at a high level. It turns out that there's some cases where you can use accessible computational tools from convex optimization to solve what seem to be intractable problems. And there's a particular regime in which that works and a boundary that we can delineate. Okay, there's a different way to look at this, which may be more memorable for people in the audience who are, say, trained in probability or in standard statistics. And it has to do with taking random points in a high-dimensional space and think of creating their convex hull, namely take an imaginary rubber membrane that sits outside of all those points and then let it shrink down until it ends up just enclosing the cloud. So let's see if I have a picture of that. So in 2 dimensions, I would have a whole bunch of points, and if I had nails in a plane at each one of those points and took a rubber band, extended it outside of so it enclosed all the points, and then let the rubber band go, what I would see is this particular outside enclosure. It's called the convex hull of the points. And I'll come back to this in a moment. So that's symbolized here. And classically, there's a phenomenon which we would expect to hold in low dimensions, which goes back quite a ways. And statisticians such as Brad Efron and probabilists such as Alfred Renyi worked on this quite some time ago. Namely, they said, how many points are there on the convex hull? And the answer is, it's not that many. It's a function that involves a log of how many points you have. And so most points are not on the boundary of the convex hull. So here you see there's a relatively few number of points out here and then quite a lot on the inside. Okay, and that's our low-dimensional intuition about convex hulls. Now, in high dimensions, things don't work that way, not at all. Instead, if you consider the case where the number of dimensions and the number of data points are proportional, and you look at the convex hull, it has a very interesting structure. First of all, with overwhelming probability, every data point is on the convex hull. Okay, there's nothing on the inside. But even more surprisingly, if you take the line segment between every point and every other point, consider any one of those line segments, that's on the convex hull. It does not, that line segment doesn't go through the middle. Now, recall in low dimensions that wouldn't be true. If I took the line segment from here to here, boom, it's going to cross through the middle. It just, you can't imagine that anything else could be true. from your low-dimensional experience. But in fact, in the particular case we're talking about here, in high dimensions, that principle fails under the setup that we're talking about. And the key point is that this continues up to the point where if we take every k tuple, that defines a k face, namely k-dimensional convex set spanned by those particular points. That continues up to a quite large k. So not only the individual points, which are zero-dimensional faces, or the pairs, which give one-dimensional faces, namely edges, we go up to quite high-dimensional faces that are all sitting on the edge of the convex hull. And the curve that we showed you before, which was, I guess, a red curve in the last one, is this blue thing. And it has exactly the same interpretation that we had in the previous case, namely there's k over n on this axis, and then there's n over p on this axis, so just as before. But now the interpretation that we're having is in terms of these convex hulls, and it's saying that every k-dimensional simplex that you can form by taking k plus 1 points, if it denotes a point that would be below this curve, then it's going to be on the boundary. And if it's above that curve, then it will intersect the interior of the set. So there's this very strange counterintuitive thing happening in high dimension. And that's completely equivalent, if and only if, to this phenomenon about linear programming being able to solve these combinatorial optimization problems. And in statistical physics, this phenomenon would be called a phase transition. Namely, we have a phase space, and as we cross a certain place in that phase space, you get a rapid change in behavior. That's exactly what has happened. So the plot that you were seeing before was an experimental determination of what we're graphing out here, which is what statisticians and probabilists would call an asymptotic relationship. That's the phase transition that's been derived. Now, we could do a similar thing with a symmetrized Gaussian point cloud. So we just generate a bunch of points from a Gaussian distribution in high dimensions, but create symmetric pairs about the origin, then take the convex hull and do similar things. A similar thing is true in low dimensions, that not many points are on the boundary. But again, a similar thing happens in high dimensions, that everything is on the outside of the set. And no pair is going to generate a line segment that touches the inside of the set at all. And there's, again, a phase diagram. There's curves that denote different events, but the one that we're mostly focusing on is this blue curve. This is slightly different than the previous blue curve I showed, because here we're considering the L1 optimization where there's no sign constraint. And previously we were considering the L1 optimization with the positivity constraint. The curves end up being at slightly different places. Okay, so let me explain how this geometry is sort of relevant to our case, or give you an idea of a little mental model that you can play with for a while, and you can decide that these phenomena are all related, and you can maybe understand what the computations are that are underlying it. Here I'm showing you a four-dimensional simplex that's being projected down into 3 dimensions. And so they're sort of these points here, and there's a point there on the interior. And so what you see is that in that projection, and this is a low-dimensional case, one vertex lands in the interior, and several faces land in the interior. Namely, up in the high-dimensional space, the four-dimensional simplex has that as an extreme point, but once I project down, it's no longer an extreme point, it's on the interior. And there's some faces that get projected to the interior. that's our low-dimensional intuition. And the model of the random point sets, Gaussian points that we're talking about, is exactly of the form that those Gaussian point clouds can be viewed as realized by taking a simplex and projecting it down. It's sort of a standard model for generating Gaussian points is doing exactly this. So the Gaussian distribution that statisticians love for modeling data is related to this geometric thing of projecting simplices. And you can look at higher dimensional simplices projected down, and you lose, generically you'll see even more points and faces and edges being lost. And what I'm telling you is that in high dimensions, things aren't lost in this way. That the picture that you're seeing doesn't happen this way in high dimensions. Points don't land in the interior when you have the relationship between the variable k, n, and p that we've talked about. Okay? Now, we could make lots more pictures, but then the question is, what does this have to do with the original problem, which is we're looking for sparse solutions of systems of equations. And for that, what you should notice is that if we have a model for a phenomenon that's sparse, very few terms in that model are active. And so we could consider all models that can be built up by allowing only 3 variables to be non-zero, namely 3, 12, and 106, and giving them some values. We could consider maybe another set of models that has, in addition to those 3 non-zeros, some other non-zeros. Those are examples of statistical models where there's some indeterminate quantities. On the other hand, the faces of a simplex have a structure that's reminiscent of that because they're determined by exactly relations that are quite similar with some other conditions that come out of the structure of the simplex. Now, the collection of all the sparse models is a partially ordered set, which is in some way very closely related to the collection of all faces of a polytope. And when we're talking about whether faces are lost in projection, it turns out to be the same thing as saying whether models are aliased when we have an underdetermined system. The projection is doing the same thing as underdetermining the system. And so the relationships between what statisticians would view as a natural collection of models and what people in geometry would view as a natural collection of geometric objects associated with fundamental Platonic solids. It's a close one, and that's what's to be exploited intellectually. So we could summarize everything up to this point by some simple results. For example, in the positivity constrained case, it turns out that the chance that these two things have the exact same solution is exactly the ratio of the number of faces that the p-1 simplex has under projection to the number of faces that it has when it's unprojected. And then the phase transition that we talked about, that diagram, is that for certain choices of the variables k, n, and p, this ratio is basically 1, so no faces are lost, and so all of those models don't get aliased, and so you can recover things. So there's a sequence of associations between objects in geometric combinatorics, in geometric probability, and random systems of equations. A similar thing happens when we don't have sign constraints, but now the object, instead of being the simplex, is the so-called cross polytope, which is a kind of generalized octahedron, but the exact same structure exists. Okay, so the takeaway messages until now are that if we have a typical random underdetermined system, if there is a sufficiently sparse solution and sufficiently is given by that curve that applies to the optimization problem, the phase transition that we documented, we will be able to find the thing by linear programming with overwhelming probability. The probability statement is talking about the draw of the matrix. In addition, and I haven't explained that here, I've only given you an inkling, the actual trade-off between sparsity and indeterminacy of the system, that the amount of sparsity you need to be able to recover when a system is so-and-so underdetermined, that trade-off has been developed using combinatorial geometry, and the sharp transition is known. A lot more can be said. I just want to say, that's the kind of math and the kind of results that one needs to understand this as an underlying phenomenon. What I'd like to do now is talk about things that some of my students and postdocs have done over the years around this theme to show you some applications. So the good news is we're kind of over the hard part. There will be more pictures, and I don't know what the bad news is, but maybe you'll let me know in questions. Okay, Scott Chen was a graduate student at Stanford that I worked with, and in his thesis he considered the following problem: concatenate together matrices associated with standard mathematical transforms like Fourier transform, wavelet transform, or just the identity transform, and make a matrix that's wide and not so tall that way. So the kind of matrices we love in undergraduate linear algebra are square, but we're not going to do that. What Scott said is, let's concatenate these together, and the term basis pursuit was developed for solving exactly the same kind of L1 optimization that we're talking about. So a standard example that was considered was the Fourier matrix, which is a matrix with a bunch of complex numbers, all of modulus 1 in it, and the identity matrix, which has 1s on the diagonal and 0s off diagonal. So there's a specific example where, with that particular case, here's a signal, and it's made up of 2 sinusoids and 2 spikes. Now, in order to tease that apart, you have the problem that any such object could be built out of sinusoids alone. That's a basic theorem of Fourier. And it could certainly be built out of spikes alone. That's a trivial fact. But there's no unique way to write this thing as a sum of sinusoids and spikes, since we can do it with either or with any kind of appropriate linear combination of either. Now, nevertheless, by applying this optimization principle, if we plot the coefficients that came out of the L1 optimization, what happens is he got the appropriate 2 spikes with the so-called discrete cosine transform or Fourier domain, and the appropriate 2 spikes that one could hope for in the spike domain, and actually teased apart the structure. So even though it was an underdetermined system, L1 minimization worked. And some other algorithms, such as greedy stepwise regression, as it's known to, well, just stepwise linear regression or forward stepwise regression, it's known to statisticians, didn't work so well. They would find all sorts of other things going on, but not the 2 and 2 structure using terms from the sinusoid and spike systems. Xiaoming Huo, in his thesis, made something that was made out of wavelets and essentially a version of what we later called curvelets. And here's an image, a cartoon by, I think it's Lichtenstein. And you could represent this using wavelets. You could represent this using the curvelet system. Both of them give you determined systems of equations. But here what's happened is you're representing them using both with an L1 optimization. And what's happened is that the wavelets pick up all the jaggies that are sort of discretization artifacts. That's fine scale. The blush in the cheeks. And all the curvelets pick up all the boundary aspects. So there's a kind of semantic separation of the image content into different layers by this device, using the fact that you can solve underdetermined systems. Jean-Luc Starck, who's at the Centre Européen d'Astronomie, but was my postdoc for a while, looked at a extragalactic image that was composed both of isolated objects and sort of a more nebular phase, and created this separation. The original image had these things on top of each other all mixed together, but the separation results by using, again, two matrices, creating a system that's a factor of 2 underdetermined, and use an L1 principle to separate those. And he's since done many other examples. Michael Elad was another postdoc of mine, and he's now an associate professor at the Technion. And he and Jean-Luc did the following in some years ago. Take a well-known picture, Barbara. Well, this is almost the well-known picture, Barbara, but there's a key difference. So Yali has probably seen this 10,000 times in his life, but there's something different from Barbara. And the point is, that's the actual well-known picture, Barbara. In this picture, there's no texture on her, right? And what's happened is that this is the component that's represented by curvelets. That's the component that's represented by discrete cosines. The discrete cosines pick up all the texture, and the curvelets pick up all the geometry. And so from this one picture, this principle of just solving underdetermined systems separates out the content types. Here's a statistical example done by my PhD student, Victoria Stodden, and this is relevant to genomics. So imagine we have a situation with many potential predictors of a phenomenon, but not so many observations. That's like the genomics example I was talking about. It comes up often in clinical medical research. Some small fraction of those are useful predictors, but we don't know which ones they are. So let's set up a situation where the observations contain Gaussian white noise, and there's an underlying linear model, and we apply forward stepwise regression with so-called false discovery rate control methods for deciding when to stop the forward stepwise regression. So the result that she got, it's actually, if you go to the Philtrans Roy Sock this month, you'll see this picture on the cover. But this is from her thesis. So what happened with the stepwise regression is you exactly see the phase transition structure, that below here, if the predictors are not too many in number relative to the number of potential predictors, everything's fine. So again, here we have the ratio between the number of observations and the number of predictors, and here we have the ratio between the number of useful predictors and the number of observations. As we move around in this two-dimensional parameter space, you see abrupt transitions in the behavior of these statistical procedures. There are other applications of underdetermined systems, and here's one for the, I suppose, non-existent engineers in the audience. But since there's no engineering school, this doesn't have the same interest that it would if I were speaking in, say, Champaign-Urbana. So maybe I'll skip it. We'll excuse that. Okay. So here's another one that's a little more conceptual. Compressed sensing, which Steve mentioned. In the orthodox view, and this is where we get to why you have to sit so long in an MRI, an image is made of pixels, and there's one number per pixel that determines the brightness that you see in that image. And so if the image is 1,000 by 1,000, there's 1,000,000 numbers that have to be determined. Therefore, you have to sample 1,000,000 things in order to get that. But suppose you know that the image, if measured in an appropriate basis, could have been generated by something sparse. Then does it really have 1,000,000 independent degrees of freedom in it? or is it just apparently made up of a million things, but in fact made up of far fewer? Well, we know that real content of the type that humans look at is highly compressible. And we use that fact every day when we download stuff from the web. It's all in a compressed format. It gets transmitted by using sparsifying transforms, either discrete cosine transform or discrete wavelet transform. So we know that there are bases for important media types that sparsify and compress. So it's actually the case that for lots of images, they do arise as sparse objects if they're represented in the right basis. So if you think about what that means, then if we make measurements on the function using a certain matrix and express that matrix in the basis that sparsifies the object, we're back to the same problem that we just talked about, namely solving an underdetermined system of equations. The question then comes down to how many measurements we need to take about the underlying object is the same as how many measurements we need to take so that this is going to find the sparsest representation, because that's the thing that we're looking for. So some time ago, I worked on this, and Emmanuel Condez, a former student of mine, together with Justin Romberg and Terry Tao, worked on it. It's sort of been canonically formulated this way. The key point is we don't need to make those million measurements if there's really only 10,000 degrees of freedom. We instead need to make fewer measurements and then solve a more complicated reconstruction formula than what the MRI community was used to. And so simple examples of this were tried, for example, in Yaki Zeig's thesis. So here's an example of a simple function that is sparsely representable in terms of what are called Haar wavelets. And if you just make, so there's an underlying number of parameters, 2,000 seemingly, but there's really only 340 non-zeros here. And if you even just make 256 measurements, that's an improvement by a factor of 8 to 1 over the nominal number. And because the object is sparse, this method can reconstruct. And we can do this with images that are blocky. This was represented. Again, the principle is there are fewer real parameters behind this than you might at first think. And similar things have been done with phantoms by Yaki. Now, Michael Lustig is an MRI guy. He's just got his PhD at Stanford. And this was, I think, the first example that he made that involved an actual physical experiment. So the idea was to speed up MRI acquisition by a factor of 8 over the standard, and then see if you could use L1 minimization on the wavelet representation. So you see that if you did the standard of reconstruction with that undersampled object, this is what you'd get. It's kind of a mess. But if you use the principles that we've been talking about, you would get something that's fairly reasonable. So very recently, there's been a lot of work on actually trying to make this a real idea in MRI, and commercial vendors are interested in it. So the things that are positive about this is that, first of all, the MRI community already sort of likes the idea of having some complicated matrix A that they measure, and they like the idea that there's a whole bunch of fancy math behind doing the data acquisition, and there's fancy reconstruction algorithms. It fits with their worldview. That might not work in other applications, but it does work for them. As a result, if you just give them a new idea or validate some ideas that they may have had before by saying, yes, you can undersample, that's really all they need to get to work. So I don't want to claim that that math actually somehow has solved all their problems. What it has done is energized them to do a lot of things that they pretty much knew how to do anyway, but they didn't believe they had permission from mathematicians to do. Instead, they thought that mathematics had these ugly things like the fundamental theorem of linear algebra that said, don't do this, it's a bad idea. Now they're hearing from, from people like me or Emmanuel Condez and so on, that actually you could, under the right circumstances, do that. And so they're working very hard on it. What I'd like to do is just switch files here for a moment to show you something. It's a paper that's to appear in Radiology by Michael Lustig, and I just want to get to the figures and give you an idea. This was things have progressed to the point where you could consider one of these L1 optimization methods using the wavelet basis and compare them with things that might otherwise be done, show them to radiologists and ask them to grade the quality of reconstruction. You would do it blindly so that the radiologists don't know the origin, they don't know the algorithms involved, they're just comparing them. And you could ask them many questions. So we could ask them, is this diagnostic? Could you actually make a decision about the organ system involved? Do you have confidence more in the result you're seeing from one picture than another? If they're both diagnostic, which one gives you the most confidence in your conclusion? And in whatever way that radiologists judge image quality, do you get better image quality by using this? Now, PI stands for parallel imaging, and that's in MRI, that's code for there's a system of coils used to gather the data. So if you've ever seen people in MRIs that have a sort of a helmet on their head, that's a system of coils in there. And then there's a different system where you don't have a helmet on your head. Is this making sense? So we're only working in the realm of all these coils are present in both methods, and we're speeding up the acquisition dramatically, sometimes factors of 7, and then we're asking, do you get a diagnostic quality image even with this acceleration? So when I say we, I'm not a co-author of this paper. This is Mickey Lustig's work together with doctors at Stanford. So they talk about a variety of structures that were looked at, and these range from things in the abdomen to knees and all the standard things that come up in radiological applications of MRI. And there were a certain number of exams that were done and all sorts of parameters. Anyway, let me just get to the key points. So the different image reconstructions I'm not going to show just for time, because I don't think the point is that you judge whether you like the picture so much. It's really what's important is, will radiologists accept this method? It really doesn't matter what we think. So in this particular case, we've got, for example, a rating of image quality. And what you can see is a lighter bar and a heavier bar. The lighter one, in these cases, is all associated with using this compressed sensing technique of L1 minimization on top of the wavelet basis. And you can see that almost all the high quality results come that way. And that almost all the low quality results come from acceleration combined with not doing it that way. So you get noticeably worse results by just trying to accelerate using the coils only that are placed in the helmet. But if you combine the coils with this compressed sensing idea, you get substantially better results. There's substantial confidence that this is a better result on the part of the radiologists. And there are a few other things worth noting here. Structure delineation. well, there were no radiologists that said 3 greater thans of the compressed sensing relative to what you get by parallel imaging. But as far as 2 greater thans, 1 greater than, or about the same, you can see that the compressed sensing technique really worked better in generating positive sentiment from the radiologist. And then there were specific things that the radiologists were very enthusiastic about in comparing methods. And in this paper, if one were interested, one could go in and talk about very particular structures that had the property that one way they could really be seen and the other way they couldn't be seen at all. So here's a comparison of a 6.3 factor acceleration. If you just use parallel imaging and you just try to accelerate, you get something very grainy, and one can't really interpret some of the important features. Here, using the compressed sensing technique, it's not grainy. Many of the features are visible, and what the radiologist is interested in seeing can actually be seen, and there's an enthusiastic response according to the researchers here. Okay, so we started out talking about random matrices, and those were matrices with Gaussian IID elements. Then we started talking about a lot of specific things that people were doing that had to do with matrices that were built up in specific ways, for example, out of mathematical transforms, or were compatible with MRI scanners. And it may seem that I'm doing a bait and switch because I'm giving you these very precise results about the phase transitions for Gaussian matrices, and then showing you applications that don't use Gaussian matrices. But there's a certain amount of universality present, namely that the exact same results are true for other matrix ensembles. And the phenomenon that leads to this is getting increasingly well understood. But we considered many different matrix ensembles that had matrices that for various applications are more practical than Gaussian ones, and some of them are enumerated here. And Jared and I did about 6.8 CPU years worth of computations, and then reduced the data through 33 pages of analysis in Phil Trans, Roy Sock. And what we found is that the transition between the L1 minimization working and not working was surprisingly consistent across all of these different matrix ensembles. So what you're seeing here is that's the curve when the coefficients are not constrained to be non-negative, when they are constrained to be non-negative. The dark curve is the theoretical result coming out of the Gaussian case. And those fluctuating curves are empirical results for actual matrix ensembles that we did lots and lots of tests with. So there is some universality class which remains to be explored, which behaves exactly like the Gaussian case. And that leads us to believe that we understand very well the sampling theorem, namely the exact boundary in the sparsity indeterminacy space that you can move right up to and still get appropriate answers by using these techniques. There are many people working actively here. Manuel Condez recently moved to Stanford. He should definitely be mentioned. And I've mentioned a few names of former students, and these are some major contributors to the subject. I should say that there's a very related topic of matrix completion in which the vectors that we've been talking about, those vectors X, become matrices X, and all the same questions can be asked there, except that we replace sparsity by low rank, and then the geometric combinatorics that we're doing based on polytopes becomes somewhat different but closely related based on ideas from algebraic geometry. So instead of dealing with simplices and so on, we're dealing with more complicated algebraic geometry constructions. I haven't been able to talk about that at all, but there are many close relationships. I mentioned a whole bunch of papers. A large number of these were joint work with Jared Tanner. He was my postdoc at Stanford, and he's now a lecturer at the University of Edinburgh in the math department. Thank you very much for your attention. Well, what we're doing is we're exploiting sparsity when it exists. And maybe there's a philosophical question. There are researchers in vision who are motivated by the idea that we have a visual system with a lot of components in it that is amazingly effective at figuring things out about the world. So researchers in vision are, typically interested in how that happens. And there's a whole group of people who work on what are called natural scene statistics and natural stimulus statistics. They have meetings and so on. And they keep identifying in one media content type after another that there's a great deal of sparsity present in that content type. So whether we're talking about bird songs or odors or the mating dances or something, they're simple patterns that we may not yet completely understand. But instead of complexity, there's actually sparsity when looked at the right way for many things. And there are people who have elevated this into a kind of philosophical principle that the world is only really comprehensible to us with our limited ability to process information because there's a latent sparsity out there and we have just the right matched hardware to understand it. So in that sense, there is an analogy because what we're doing is we're saying, in this imagery there's a latent sparsity and we don't need to make as many observations as linear algebra would naively say if we can only exploit the latent sparsity that's there. Now that exploitation requires knowing something about a basis or a representation which expresses the sparsity, and it involves knowing some math which allows us to exploit sparsity such as L1 minimization. Actually, I should have mentioned your question. I was told to repeat your question, but I'm sorry, I forgot. I'll try to do that next time.
Is there another question? Mike?
Michael Stein asked a question of, is there a way of knowing when the L1 solution is equal to the L0 solution? So what we've been talking about here is sort of the hydrogen atom of these things. It's a very simple version of a notion of sparsity. And in this particular case, the answer is yes, because if it happens that you get a highly sparse answer with fewer than n over 2 non-zeros, it must be the sparsest answer. Okay, that's just a fact about matrices whose columns are in general position. There are more general notions of sparsity that involve not that strict separation into zero, non-zero, but things where sort of there's some big guys and then there's littler and littler and littler, and for those it's more problematic. But typically what happens is when L1 fails, the answer doesn't look sparse, and you can't mistake what you're seeing for the kind of condition that would make things successful. That's not a theorem, no one's proved it, but no one has ever observed it to fail in a way that it produced a sparse result, and that fooled us because it was the wrong sparse result. Perhaps that would be a fun project, try to invent one.
Say thank you very much, David, for a stimulating talk on some wonderful work, and for congratulations again on your honorary degree. You are now of the University of Chicago.